Hello and welcome to today's webinar, Predicting Reactivity to Drug Metabolism Beyond P450s, Modeling FMOs and UGTs. My name is John Norman and I am the moderator for today's webinar. Okay, so now time to hand over to our presenters from Optibrium, who today are our principal scientist, Mario Uren, and our CEO, Matt Seagal. Matt, I will hand things over to you.
Thank you very much, John. It's a great pleasure to speak with you all today. Thank you all for joining us. It's also a great pleasure to welcome Mario to the webinar. Mario is our leading, or has been leading our drug metabolism research at Optibrium and working on the exciting topics that you're going to hear about in a moment. And what he's going to describe to you today is actually the culmination of over 3 years of very hard work. And so I thought, Mario, before we get started with the main presentation, maybe you could just tell us a little bit about the research project and how it progressed.
Yes, of course. Thank you. And hello to everyone who's listening. So obviously this project wasn't a project for only one person. And I should say that I myself, I was focused mostly on UGTs and the mechanism of UGTs and how to build the site of metabolism models for UGTs. And also the UGT project was a collaboration between Optibrium and LASA Limited. So I should say thank you to all of the nice people from LASA who have helped me along the way. Now, most of the work with FMOs was actually done by Peter Walton, who should actually sit amongst the audience. And he was with us for 1 year, and that's because he was an intern, or I think the official name for that was industrial placement student, and he was from the University of Nottingham. And of course, I've been getting a lot of help from my colleagues, Rasmus Leth, Peter Hunt, our Director of Computational Chemistry, and of course you, Matt.
That's very kind of you, Mario. That's great. So I think with a little bit of background there, it's over to you to tell us more about predicting drug metabolism beyond P450s. So go for it.
All right, thank you. And so I thought that we should start with a small overview of today's webinar. So I'll start with the background on FMOs and UGTs and why we chose those enzyme classes and what do the acronyms actually stand for. And then for a few slides, I will give the microphone back to Matt, and he will talk about the different approaches to predicting drug metabolism, and also he will focus on the reactivity accessibility approach, which we'll be using in this work. And I should also say that the current P450 models in StarDrop are also built using the same approach. And Matt will talk about it a little bit more, why we need mechanistic studies, but once he's done that, then I will talk about the density functional theory studies of both FMOs and UGTs, and also obviously we want to use those models in our everyday work, which means that we cannot wait until the density functional theory calculations finish. So I'll also shortly talk about how we translated those results from DFT to the world of semi-empirical methods. And in the end, I will talk about the site of metabolism models, how we took the results from the mechanistic studies and combined them with steric and orientation descriptors, the accessibility part of the approach, and also show you a few examples of the models we put together. And let's start with the background of FMOs and UGTs. FMOs will be the first enzymes. And FMOs actually stand for Flavin-containing Monooxygenases. And we'll talk about the flavin part a little bit later, but in general, FMOs work in conjunction with cytochrome P450s in the modification phase. Now, like cytochrome P450s, FMOs have many different reaction types, but in our case, N and S oxidation are by far the most prevalent reaction types in humans. And on the right here, you can see a few common substrates for FMOs. And in our work, we will be concentrating on the N and S oxidation reaction types only. And FMOs have only 5 isoforms, and we'll be concentrating on FMO1 and FMO3 because those are the isoforms which are actually responsible for the metabolism of drug-like molecules. Now, the rationale to choose FMOs, amongst other enzyme classes, was because they have overlapping substrates with P450s, and often they kind of get overshadowed by P450s, which means that sometimes when you could have a great drug-like molecule, but you know that it's only going to get metabolized by one P450 isoform, then you could run this model and see, hey, maybe this also gets metabolized by FMOs, so you might avoid these drug-drug interactions. But maybe you want to prevent the P450 metabolites on all, so what you might do is you might kind of gear your molecule towards the FMO metabolism. And of course, when we talk about FMO metabolism, then we have to also be careful because some of the metabolites can be extremely toxic. Now, the UGT stands for Uridine Diphosphate Glucuronosyltransferase, and a very complicated name, and it's an enzyme class in the conjugation phase. So 40% of known conjugation reactions concerning drug-like molecules are metabolized by UGTs, and 15% of all of the drug metabolism reactions are metabolized by UGTs. And as a quick reminder, I think cytochrome P450 is metabolized approximately 70 to 80% of drug metabolism reactions. There are fewer reaction types for UGTs. There's N and O glucuronidation, which are by far the most prevalent reaction types. And in humans, C and S glucuronidation have been reported as well. But they're not that common, and in our work we have only concentrated on N and O glucuronidation. And for those of you who don't remember how it works, then UGTs have a cofactor called uridine diphosphate glucuronic acid, and this glucuronic acid here during the process is transferred from the cofactor to our substrate. And you can see the metabolite here could be easily soluble in water and easily excretable. Now the isoforms, UGTs have way more isoforms than FMOs, and we had to make some kind of a choice here. So we chose the isoforms 1A1, 1A4, 1A9, and 2B7 because first of all, they are prevalent in the liver, but also they are known to metabolize drug-like compounds. And the rationale for choosing UGTs is that obviously they're the most important enzyme class in the conjugation phase. Now, before we continue on with the mechanism studies and the cytometabolism models, I would like to give the microphone to Matt, and he could talk to you about the approaches to predicting drug metabolism and the approach we're going to use. So over to you, Matt.
Many thanks, Mario, for that introduction, and thanks for handing it back to me for a moment. I just thought it would be good to provide a little bit of context about sort of the previous work that we've done and our sort of overall philosophy behind predicting drug metabolism. And really, you can think of the different approaches as sort of occupying a spectrum, where at one end of the spectrum, you can see these sort of empirical methods, which are based around statistical modeling, machine learning, and all good buzzwords like artificial intelligence and stuff like that. Where at the other end of the spectrum are the more mechanistic methods, really based on trying to understand and model the mechanism leading to the drug metabolism reaction. And it might use methods such as molecular dynamics or quantum mechanics, as we'll see in a minute. And there are different pros and cons of these methods. So in terms of the empirical methods, the pros are that they're very fast. They're relatively fast to build, and in particular, they're very, very fast to run on a new compound. The cost of the calculations is very low. They're also fairly easy to set up. There are lots of different machine learning methods, and setting those up and building a model is relatively straightforward if you know what you're doing. But the downside is typically they need a lot of data. Metabolism is a very complex process, and so we need a lot of data to understand the patterns within that data for the machine learning methods to really be able to dissect that information. They also tend to be quite non-transferable, by which I mean they're trained on a specific area of chemistry, specific classes of compounds, or particular types of sites of metabolism. But if you, ask it to make a prediction for quite a different compound, then it's moving outside the domain of applicability, and the accuracy of those predictions will diminish very, very quickly. And they also tend to be quite qualitative. So there are big uncertainties in the prediction. Sometimes you simply end up with a classification, or at least not a very clear distinction between different sites. Again, at the other end of the spectrum, if we're looking at sort of mechanistic methods, then the pros there are that they can be built with smaller data sets, although you do need very high quality data sets. And they tend to be very transferable. So they're based on physical principles, the fundamental sort of underlying principles of chemistry and physics, in particular, as we'll see, quantum mechanics. And so really these data sets aren't used to fit a model, but they're much more used in order to sort of validate the results coming out of those sort of physics-based principles. And they're at least, I guess you might call semi-quantitative. So they're not necessarily perfectly accurate in every case, but because we're actually looking at mechanisms and we're trying to estimate the reaction rates and so on, that they tend to have a higher degree of accuracy, or a greater confidence. Now, the downside is they can be slow, and in some cases very slow, particularly when we're talking about methods like density functional theory. It may take hours or potentially even days to perform a simulation. And setting up these models requires a really detailed understanding of the mechanisms so that you know that you're modeling the sort of the relevant pathways and mechanisms. And as you'll see, that's been a large part of the work that Mario, Peter, and others have undertaken in the case of UGTs and FMOs. And really, our belief is that the sweet spot lies somewhere in the middle of these two. What we want to do is get the best of both worlds if possible. We want to use a mechanistic understanding to motivate our models, but try to get at least some of the speed of the more empirical methods. So really trying to blend the two and get the best of both. So the approach that we take can really be described as a combination of reactivity and accessibility. And really that's motivated by these two factors that govern the sites of metabolism and the reaction mechanisms for these different enzymes and different isoforms. So first of all, we look at the electronic properties of the substrate. We're trying to model the reaction mechanisms and understand the energetics. This will depend particularly on the structure of the substrate and the reactivity of those different sites to the reaction mechanism of metabolism by that enzyme. And what we would expect to see is that the rate of product formation is correlated with the activation energy of the rate-limiting step in that reaction. And again, because these different classes of enzymes within each class have a very common mechanism between the different isoforms, we would expect that to be independent of the isoform. We're modeling simply the raw reactivity. And as Mario said, this approach has been used for many years in our P450 metabolism models. So these are part of the P450 module within StarDrop, and we've been developing those along with colleagues over 20 years now. And essentially what we do in our P450 models is to estimate the activation energy of that rate-limiting step, governing metabolism, in this case by cytochrome P450s. We model this both for hydrogen abstraction reactions, that leads to aliphatic hydroxylation as well as N and O dealkylation, but also direct oxidation reactions. And this sort of illustrated here is an aromatic oxidation, and the sort of reactive species within P450s is a so-called compound 1, and here you can see as it moves through the transition state, which is the tetrahedral intermediate, we can calculate the activation energy and eventually move on to the formation of the product. And it's really that activation energy that governs the rate of product formation at different sites of metabolism. And here you can see an excellent correlation between the difference in activation energies between two sites within the same compound and the ratio or the log ratio between the relative rates of product formation at those sites. This were calculated in this case with density functional theory. So the electronic properties, as I say, is based upon the really detailed mechanistic understanding of the reaction, high quality predictions, and is independent of the isoform. But we do know that the metabolism, the sites of metabolism, are very strongly dependent on the isoform, and of course that really is down to the impact of the different binding sites of those isoforms, and particularly the orientation of the substrate in the active site, and hence the accessibility of those sites to, in the case of P450, that highly reactive oxyheme compound 1. And this can be governed by the interactions between the protein and the substrate, particularly electrostatic interactions, hydrogen bonding, and so on. We also need to think about the flexibility of those different isoforms, particularly something like 3A4 has a great deal of flexibility and hence a great deal of freedom to move, particularly for smaller substrates. And it can also be dependent on the size constraints and the steric bulk of the substrate itself. So this is something that is dependent both on the isoform and the substrate. And these orientation and accessibility terms can be modeled in different ways. You could take, for example, a structure-based approach and look at, say, docking of those different substrates to a model of the P450 in this case. But in our case, what we found to work at least as well as docking and at a far lower cost is to actually take a ligand-based approach. So what we do is we perform corrections to the activation energies for each of the different isoforms that we model. So the activation energies come from the reactivity, the mechanistic model, and in the case of P450s, we actually model 7 different isoforms, and these are modeled using sort of 2D descriptors. Essentially what we do is we look at the distance from the potential site of metabolism to sort of key functionalities within the molecule. So it might be the distance to a hydrogen bond donor, acceptor, a particularly lipophilic group, a charged group, or so on. We also look at the relationship to, say, ring systems, linkers, and bulky groups that might cause steric hindrance and hence limit the accessibility to those sites. Now here's where the statistical modeling becomes very, very important, because what we need to do is combine these different effects into an overall model. And so we train statistical models based on very high quality regioselectivity data sets. And so you can see, for example, the number of molecules in each of the data sets for the 7 different isoforms that we model in the case of P450s. Those of you who are familiar with the field will know that there are actually published data sets that are significantly larger than this. But quality is key, and so in those cases we actually went back to every single reported data set, went back to the original publication and checked the quality of that data set, the data point. We looked at the particular assay that was done, the concentration of the substrate. In some cases, in fact, the isoform had been misassigned, and so really we focus down on those data points that have the highest quality, which enables us to capture the strongest signal. And just to show you how this works, this is the validation result on an independent test set of over 30% of the full data set. All the details of these models are actually published in our 2017 paper by our former colleague John Tyzak and colleagues. And this is just a snapshot of the validation that we did, but this is showing the performance in terms of the top 3, top 2, and top 1 prediction. So top 3 means at least one of the top 3 predicted sites is observed experimentally, and you can see that's the case in, well, I would say 90% for every single isoform, but in fact 1A2 is only 89%, so just under that. Top 2 in this case is 85% in every case, except for 2C8, which is, I think, 83%. But you can see a very high quality level of prediction here. and the sorts of information that you can get. So here's an example of the prediction of metabolism by both Venlafaxine, by both 3A4 and 2D6. It's a substrate of both of those isoforms. So here you can see relative proportions of metabolism at each position, and here you can see for 3A4 the predominant site of metabolism is predicted to be here at C12 and C13, which would give you an N-demethylated product, where it's perhaps a very minor metabolite might be due to O-demethylation here at the methoxy group, whereas 2D6 is almost exactly the opposite. The vast majority of metabolism is predicted to be here at the methoxy group. And we can understand this. Both of those sites are highly reactive, but this is an orientation effect within 2D6. We know that aspartic acid residue 301 tends to bind basic nitrogens and orient them away from the oxyheme. So these sites are far less, these sites around the nitrogen are far less accessible to metabolism in 2D6 than the methoxy. So that's a sort of illustration of the results you can get. Of course, having predicted the sites of metabolism, you can also say what the resulting metabolites are likely to be for each of those sites. So you can get a feeling for the products that you're likely to see. Okay, so that's just an illustration of the principles that we're talking about here in the case of P450 metabolism, something we've been doing for very many years, something that has been very widely studied for very many years. But I'm going to hand back now to Mario, who's going to tell us about how we can take these same principles and generalize them to other classes of enzymes. So back to you, Mario.
All right, thank you. The rest of the webinar kind of goes in two sections. The first one is the mechanism of both FMOs and UGTs, where I explain how we get the activation energy, which Matt just told us about. And the second section, we'll talk about the steric and orientation descriptors, and I'll show you a few examples of the FMO and UGT models. But let's start with the FMOs. And like I said before, we're going to concentrate on N and S oxidation, and like I said, we'll talk about a little bit about the flavin-adenine dinucleotide. So this is the cofactor for FMOs, and this essentially does the oxidation part, but it cannot do the oxidation before it forms FAD peroxide. So you can see this here is the just the FAD, and the peroxide is formed here. And when we look at the catalytic cycle, then we are actually interested only in this red part, where the one of the oxygens, this oxygen over here, gets transferred to our substrate. So we're only going to be modeling this red part here. And of course we started from the literature, and it seemed that in the literature there are conflicting reports. One of the papers suggested that this reaction mechanism is radical, and the other one suggested that no, this is SN2. So our job here is to model the rate limiting step using density functional theory, and also make sure it's going to be SN2 or radical. And before we talk about the reaction mechanism, I also wanted to say that Matt already told you that in the first instance, or if you look at the pure reactivity, then we'll kind of ignore the protein and we'll add the protein back in during the accessibility part. But also the full FAD-OOH or FAD peroxide is way too large for practical calculations. And we actually know from the experiments that the tail, and by tail I mean this part over here, is buried in the groove of the protein and does not interact with the substrate at all. So we thought, can we simplify our reaction mechanism a little bit by removing this tail? So we did essentially two experiments, but at some point we decided that, hey, wait a minute, can we simplify it even more when we would remove the benzene group here as well? And we did the experiment by studying the behavior of the simplified system compared to the full system. And essentially we elongated the oxygen-oxygen bond length in the peroxide. And as you can see, for both three cases, the behavior is pretty much the same. So we were safe to assume that yes, We don't need the full tail in our calculations, and we went on and did our reaction or mechanism studies with the simplified system. Now, I'm not going into too much detail with the radical versus SN2 transition state, but all of our tests and experiments showed that this has to be an SN2 transition state, or sorry, reaction mechanism. And if you look here on the right, Peter Walton has actually put together a nice video which kind of explains how the reaction mechanism works. And I'm just going to press play here. And oh, I should say that this is 3-methylamine TMA. This is a very common substrate for FMOs. And what happens is that when it gets close to the FAD peroxide, then obviously the peroxide bond elongates, but the protein here gets anchored to the carbonyl group here. And now the oxygen gets carried over to our substrate, but the protein goes back to the FAD, which is now FAD hydroxide. And if we go left of the slide, then you can see actually the reaction coordinates. And this here, I'll switch back to the laser pointer. This here is our reactants, and the transition state actually for this reaction is 61 kilojoules per mole. And we also calculated the product energies, and interestingly enough, with a smaller basis set, the difference between the products and the reactants was 32 kilojoules per mole, and with a fancier basis set, we got 56 kilojoules per mole. And our theory is that the fancier basis set is better at kind of describing the sweeter ionic nature of our product, but actually what we're interested here is the activation energy of the transition state, and in both cases it was around 61 kilojoules per mole. So we didn't pursue this line of research any further, and we took our reaction mechanism, and of course we wanted to validate the reaction mechanism. So what we did, we chose 5 different compounds which are known to be experimentally observed to get oxidized by FMOs. And we chose those 5 so they, first of all, they would be very small, so we could negate the effect of the protein environment. But also we wanted compounds which have 2 or more potential sites of metabolism, so we can see that if we calculate the activation energy for every potential site of metabolism, does the energy predict the site of metabolism? And in all 5 cases, so A, B, C, D, and E, the site which was observed experimentally also had the lowest activation energy. And of course one could argue that, well, in the case of D, the 62 kilojoules per mole versus 70 isn't a huge difference, but that's where the steric and orientation descriptors kick in and say, okay, actually nitrogen is the experimentally observed site of metabolism. Now, before we go to the steric and orientation descriptors, we of course want to see the reaction mechanism for UGTs as well. And the story here is fairly similar. We started out with the literature study, and UGTs had a lot of experimental studies, but all of them proposed slightly different reaction mechanisms. But when you start looking at the studies time-wise, then they seem to be converging into this reaction mechanism, what you see on the right here. So we have our substrate, and in this case it's a phenolic oxygen here. And this is our cofactor, uridine diphosphate glucuronic acid. And the substrate here, the oxygen, attacks the anomeric carbon of the glucuronic acid, forcing the uridine diphosphate to leave. And the reaction mechanism is stabilized by the protein. There's the proton acceptor and proton donor, and the proton donor gives the leaving group a proton, and the proton acceptor accepts the proton from the substrate. But to our surprise, there were no previous studies using quantum mechanical modeling methods. So that is essentially what we did. And I should also say that we did a little bit of simplification with the cofactor of UGTs as well. So instead of this big molecule, we ended up with the glucuronic acid with the small methoxy group over here. And the way how we did it was fairly similar to the FMO, so I'm not going to repeat myself with UGTs here. And the reaction mechanism, which we in the end decided, okay, we're going to use that, is very similar to the one which you already saw. So this is paracetamol here, and it is also a common substrate for UGTs. And the oxygen here attacks the anomeric carbon, forcing the methoxide group here to leave. And what you could notice is that we're missing the histidines, we're missing the proton transfer. And based on our experiments, it is true that the proton transfer stabilizes the reaction mechanism, but in our case, it systematically lowered the activation energy. And if it did that systematically, we can take that into account later with leaving out the histidines and simplifying our reaction mechanism, which equals shorter calculation times. Now, with UGTs and the validation of this reaction mechanism, we took a step further, and instead of just comparing the sites of metabolism, what we wanted to do here was what Matt already talked about earlier. So we took the activation energies for different sites of metabolisms, different sites of metabolism for different molecules, and compared them with the Vmax, the maximum reaction rate. And yet again, we tried to negate the effects of the protein environment by choosing compounds which are very, very similar to each other. So in the case of UGTs, we ended up using 6 flavons. So the backbone of the flavon is here, this one. And those 6 flavons had altogether 11 experimentally observed sites of metabolism. Now you can see the correlation is pretty good, but we have 1 or 2, maybe 2 outliers here. And we were wondering, why are those 2 sites the outliers? And in experimental papers, people have noticed that if the UGT substrates sometimes have a specific group, like for example here the hydroxy group on the 6th position, if they have a specific group, then the metabolite tends to get stuck in the active site. So our theory is that both the sites 4' and site 6 belong to one of the flavons which had a hydroxy group in the position 6, and it was the only flavon which had the hydroxy group there. So our theory right now is that those 2 outliers are because essentially the metabolite got stuck in the active site, effectively lowering the experimental reaction rate. Now this of course is for O-glucuronidation. Unfortunately, we didn't find enough molecules which are very similar for N-glucuronidation, so we did something similar what we did with FMOs. I'm going to show you one example here. And as with FMOs, with this example at least, the activation energy of the experimentally observed site of metabolism was also the lowest. Now I should say that this is not the case every time, but in most cases it is, and it should be corrected by the steric and orientation factors, as Matt already pointed out. Now, before we go to the site of metabolism models, I would also like to give you a quick example how we transitioned from the DFT world to semi-empirical world. And I'm going to show you this example based on UGTs because essentially it's the same for FMOs as well. So in order to do that, what we want to do essentially is take the DFT calculations and replace them with semi-empirical calculations, in our case the theory AM1. And in order to do that, you have to consider a few things. First of all, AM1 is unable to detect weak interactions. So for example, proton transfer. So we felt really lucky to leave the proton transfers out from the UGT reaction mechanism. but also you have to take into account that AM1 is known to make systematic errors. And I have 6 examples here, 3 from O-glucuronidation and 3 from N-glucuronidation. And you can see that if we calculate the activation energy with DFT and with AM1, then O-glucuronidation, you can see it correlates pretty well. Now, if you look at the primary, secondary, and tertiary amines, they do not correlate at all. So, and this is a prime example of a systematic error. So in DFT, you can see that the activation energies range from 200 kilojoules per mole to 350 kilojoules per mole, while in AM1, they range from 300 kilojoules per mole to 450. So in order to fix that, what we did was we separated each type of site of metabolism and calculated correction factors based on these calculations. And after we have applied those correction factors, then the DFT and AM1 correlate pretty well. So here are all of the points. So now the next slide, I will start showing you the site of metabolism models. And I should say that all of the activation energies in those models are now calculated with AM1. And just as a reminder, what we're trying to achieve here are isoform-specific site of metabolism models where we combine activation energy, which came from the AM1 calculations, with site-specific or rooted descriptors. And just as a reminder, so this is a common UGT substrate. We have 3 potential sites of metabolism here, and obviously we're going to calculate the activation energy for all of those 3 sites, but also we're going to use site-specific descriptors, and a very, very simple example here is aromaticity 2. So how many aromatic carbons are there 2 bond lengths away from the site of metabolism? And 1, 2, so there's the first one, 1, 2, there's nothing here, and 1, 2, this carbon isn't aromatic either. So the descriptor is 1. And we can use hundreds of those descriptors. And in order to build the model, we use Gaussian processes. And let's go to the model. So I am going to show you the site of metabolism model of FMO3. And before we go to the results section, I just wanted to say that we considered only compounds which are known to be oxidized by FMO3s, and also compounds with 2 or more sites, because we want to make sure that we can differentiate between sites within one molecule. And the training and test sets were split by molecule. It was an 80-20 split, and we used a Tanimoto coefficient of 0.7. And training set, 54 molecules, 173 sites, and the test set featured 37 sites. And you can see there, here are the model statistics. We use a kappa value to say if our models are good or not. So we would expect the kappa value to exceed 0.6, then we're happy. Then we say that it's a good model. And for people who want accuracy, accuracy is also here. And the confusion matrix over here shows that yes, we were pretty good at predicting sites which do get metabolized and sites which do not get metabolized. And essentially here on the confusion matrix, what we want to see are big blobs here, and small blobs here, and it would be best if there wouldn't be any blobs over here. For UGTs, I'm going to present to you the UGT1A1 model, and the setup for UGT models was the same. The training and test set were a little bit bigger, and the kappa value was 0.65, a little bit lower than the FMO models, but we're still happy. And as you can see, the big blobs are in the right place, and the small blobs are also in the right place. So yeah, this is essentially it. These are the models. As for conclusions, Optiprium now has reactivity accessibility models for P450s, and if I'm not mistaken, it is for 7 isoforms. There's 2 models for FMO isoforms, FMO1 and FMO3. And for UGTs, we have 4 models, UGTs 1A1, 1A4, 1A9, and 2B7. And today I presented to you the simplified mechanism for reactivity for FMOs and UGTs, and it is also our intent to publish this work. So yeah, and the reactivity accessibility models, I showed you 2 examples, but the kappa values for all of the models are here as well. So by far the highest kappa value here is for FMO1, which is 0.94, and UGT kappa values range from 0.62 to 0.66. So yeah, yet again, I would like to thank you for listening to me. And also I would like to thank Peter Walton for doing a great work with the FMO metabolism, also Peter Hunt, Matthew Siegel for helping us. And of course, regarding UGT metabolism, I would like to thank David Ponting from LASA Limited. And of course, I should say that the funding for the UGT metabolism project was from LASA Limited. So I think that's it. That's for me. I will give it back to you, Matt.
Thank you very much, Mario. That was a fantastic presentation, really very interesting and very impressive results. So we're now on to the sort of Q&A session. I can see some questions are already coming in, but I can imagine other people are typing furiously. So while we're just giving a chance for everyone to type in their questions, maybe you could just give us a little update on the status of the research and where we're standing in terms of product development.
Yes, I think I should be really explicit with this one. The models are not yet in the StarDrop software. So hopefully within the next months we will pass them on to the development team, and then we'll get the timeline when those models can actually be implemented in StarDrop. Of course, in the meanwhile, I am going to work on other enzymes. People have asked us aldehyde oxidases, so I think that is up on my list. And of course, if we're talking about the second phase or the conjugation phase, then I believe sulfatransferases are a big thing as well. So we're moving that direction.
Fantastic. Well, thank you very much for that update. I mean, I think it is important that this is research. I mean, this is really sort of blue skies and cutting edge stuff. The next step is to take these great results and turn it into a product that everyone can run conveniently from their desktop through StarDrop. Fantastic. Well, gosh, we've got a lot of questions here. So I'm going to try to work through them, and we'll get through as many as we can in the remaining time. Not surprisingly, the first questions actually came in during the P450 calculation, P450 section of the presentation. So the first of those is for CYP reactivity with quantum mechanics, is it certain that the formation of compound 1 is the rate limiting step? And I guess I should probably cover that one off. It would be a little bit unfair to pass that buck to Mario. So yes, it's pretty well established that that is the case. Now, one needs to be careful what we mean by rate limiting step. The P450 catalytic cycle is very complex. There are 2 reduction steps. There's the binding of molecular oxygen. There's the cleavage of that molecular oxygen by 2 protonations. And so there's a whole series of different steps. And in fact, in terms of the overall rate of metabolism, the rate limiting step for the overall catalytic cycle is often actually the reduction steps, the transfers of the electrons. However, when it comes to product formation, that final step that determines which site will be metabolized, then it's that interaction with compound 1, either through hydrogen abstraction or through that sort of direct oxidation that determines the relative rates of product formation. So that's pretty well established. Someone else asked, just to keep on the P450 theme, is this blended approach the one used in StarDrop P450 module? Yes, absolutely. That is one that is exactly the method that we've been developing for over 20 years. We continue to evolve and improve, and has been part of the P450 module for many years. And that's the sort of approach that we think has the greatest fidelity by combining that sort of mechanism with some statistical modeling. Right, okay, let's move on to some FMO questions. Are FMOs found in the plasma as well as the liver?
Ooh, that is a good question. I know for sure that they are found in the liver. I am not sure about the plasma.
Yeah, I think they're widely distributed in many different tissues, but I believe that they're primarily in liver and other tissues. But I don't know that 100%. I must admit. I don't know if Peter Walton's still on the line, who's our FMO expert. If you want to type the answer in to the chat, please let us know. Okay, well, you've answered a few of the questions, but I'll just to reiterate that the question came in, are these modules now integrated in StarDrop, and in which module, and do you have plans to add aldehyde oxidase models? So I think you covered that, but it might be worth just clarifying that, Maria.
Yeah, I think that's an interesting question because right now we have the P450 module, and I guess in a way this is also a business question. Is there going to be an overall metabolism module, or are other enzymes going to be added to the P450 module? I guess this is a question for you. Regarding the aldehyde oxidases, yes, aldehyde oxidases is actually the enzyme I am working on right now. So you can see a presentation about aldehyde oxidases in the near future, I hope.
We like optimism. So yes, just to clarify the business question, it is our intention to generalize the P450 module into a more general metabolism module covering a wide range of different enzymes and other isoforms. And in fact, that leads on to a very nice question as well, which is, can we comment on the prediction of the fraction of metabolism by different enzyme classes or isoforms?
Yes. So this has actually been an idea of us as well, since now we have many different data sets regarding different enzymes. So yes, this is definitely on our list, but since I haven't really worked on it, then I can't say for sure like 100%, but we're thinking on it.
Yes, and I should say that you know, in the case of the P450 models, we have what we describe as our which P450 model. So what that does is it looks, it actually predicts which are the isoforms of P450 that are most likely to be responsible for metabolism of your compound. And you could imagine generalizing that to a which enzyme class, and maybe a tree of models where you just pick the enzyme class that's most likely, or classes, plural. That might be combinations of two, and then within that, which of the individual isoforms are likely to be responsible for metabolism, hence predicting the sites of metabolism and the eventual products.
Yeah, and I should add that we have played around with the which UGT models, essentially for picking the four isoforms we have right now, and it seems that they are working.
Indeed, yeah, that's looking like some very promising results, but not early enough, not far enough along to really sort of present the final conclusions.
Yes.
Wow. Okay. Let's see. I'm trying to maintain some themes here. I'm just looking down lots and lots of different questions. So let's move on to some UGT questions then. This is a great question here. In the UGT models, you replace a phosphate, which is a good leaving group, with a methoxy, which is not a good leaving group. Were you surprised that it worked?
Yes, that is an excellent question. Yes, that is true, and I wouldn't expect it to work in real life, but since we can use the magic of computational chemistry, what it actually means is when we take the methoxy group, then the activation energies are systematically higher. So we tried the same thing with phosphate groups, and the methoxy and phosphate groups, they correlate, but methoxy groups are always systematically higher. So that's why we were confident enough to check out the phosphate group and add the methoxy group.
Excellent. And the next UGT-related question here is, can you elaborate further on the ability to correctly identify O or N glucuronides?
Yes. So what we've done here is when we calculate the activation energies, then the activation energies will be in the same range for both N-glucuronides and O-glucuronides. And what we do in our final model is we don't, how would I say that? We put all of the sites of metabolism into one model, so we don't discriminate between sites. So we treat all sites as equal sites. And the model itself, it essentially, it doesn't know if it's an oxygen or a nitrogen, but what it does know, it knows the activation energy for that specific site, and it has a rough idea depending on the steric and orientation descriptors. So does that answer the question?
I think so. I mean, I think it's a matter of that sort of generalization between using the quantum mechanics, because it doesn't really need to know what type of site it is, really. It's the activation energy that matters. And as you showed, Mario, once you apply the sort of systematic correction to the AM1 systematic error, then actually there's a very strong correlation between both N and O glucuronidation. So those activation energies generalize very, very nicely.
Yeah, and I maybe should also add that in both the trading and test sets, the reaction types are pretty balanced. So obviously you're going to have a lot of phenols and so on and so forth, but there is a mix of everything. So yeah. And it seems to work great when we kind of mix all of the site types together. And this is exactly what we actually want, right? We don't want to discriminate between sites.
Yeah, absolutely. Absolutely. Oh, here's another great UGT question. Can you develop the UGT model to predict how reactive an acyl glucuronide product is?
Yes, that is also a great question. This is something we also want to do. I just haven't had time for that. So essentially, when we have that metabolite, and if it is kind of dangerous or reactive, then what we want to do is we want to raise a flag that, hey, this is the potential metabolite, and this is also potentially toxic. So we have looked into the journals or experiments, but unfortunately there's not a lot of publicly available data, at least to my knowledge, but we're definitely also looking into that. So that is a very good question, yeah.
Fantastic. So I think there's another UGT one. Does the UGT model differentiate between alcohol and carboxyl reactivity?
Yeah, I guess it does in the sense, like, for example, if you have both alcohols and carboxyl groups in one molecule, then yeah, it shouldn't have any problems because, like I said before, we put all of the sites of metabolism into one model, and the model actually doesn't know if it's a carboxyl or is it an alcohol or a phenol, and it all depends on the activation energy and the steric and orientation descriptors.
Yeah, absolutely. So let's give FMOs some attention. And first of all, Peter, thank you very much. Peter Walton in the audience there, who did most of the work on the FMOs, has very kindly answered the earlier question about the presence of FMOs in the plasma. So he says other tissues that FMO isoforms can be found in are the lungs, kidneys, and brain. But he does not believe they're found in the plasma. So many thanks for chipping in with that, Peter. It's great to have the expert in the audience. Okay, so let's have a quick look for FMO questions down the list here. How would you know if oxidation was FMO or P450?
That is a good question. I guess this comes down to the previous question, are we going to build models which say that a site gets metabolized either by CYPs or FMOs? And the honest answer is I don't know yet, but this is definitely something we have to thoroughly think through and test. in order to be confident and say, yes, this is an FMO or this is a SIP.
Yeah.
But if you're talking about experiments, then I've read the experiments, and they're very complicated experiments in order to differentiate between those two. So yes, it is a complicated topic.
And I think it's even true to say that for a long time FMOs weren't recognized as being important because the products were thought to be due to P450 metabolism. So it's a non-trivial question from an experimental perspective as well. Okay, how reasonable is it to assume that the mechanism of radical versus SN2 for FMOs is the same for all substrates?
Yeah, that is a good question. I think in the long run, if the validation data agrees with our experiments, then we can be fairly sure. But I guess we can't be 100% sure ever. So yeah, Matt, maybe.
Yeah, I mean, I think that's the fair point. Is that you know, in all of the modeling, as Mario showed you, across a diverse range of substrates, we've used the activation energies based on the SN2 reaction to make that prediction. And as you can see from the validation results, you know, it generalizes very well. You know, the FMOs, in fact, had a very high, the very high kappa value indeed. So based on that sort of empirical evidence, it looks like that those SN2 energies are sort of the determining factor, if you like, in the relative rates for different sites. I think it's also fair to say that, sorry, you weren't, in all the exploration, it wasn't possible to find a transition state for the radical mechanism, which would also give some evidence that that's probably not an accessible pathway.
Yeah, I was just going to say that I think Peter Walton spent a good month, at least, if not more, trying to find the radical mechanism, and with all of the quantum chemistry methods we had in our hands, we just couldn't, it never converged, but it always converged to an SN2 reaction mechanism really easily. So I guess that is also a pretty good evidence. Absolutely. And of course, in the paper, we are going to explore this more. So if you're interested, then yeah.
Wonderful. I will give you, I think we're just about to run out of the official allotted time, so we're happy to stay on the line and answer some additional questions. But I think just before we do that, let me just wrap up the webinar in general, and then anyone who wishes to stay on the line, we'll try to get through a few more questions before we log off finally. So I just wanted to remind everyone that we have another webinar coming up on a very different topic. It's on the 28th of April. This is about practical applications of deep learning to imputation of drug discovery data. This is a really exciting area where we've been working with our colleagues at Intelligens to apply the Alchemite method, which is a method for imputation that applies to sparse and noisy data. We published a paper on this, proof of concept, just over a year ago, and since then we've been embarking on a whole series of different applications in collaboration with many different companies in many different areas of application. And we're very grateful that of the first of those that we're able to speak about publicly was in collaboration with Constellation Pharmaceuticals. And we're going to be joined by Julian Lavelle, who is head of chemistry at Constellation, and my colleague Ben Irwin, who did a large part of this work in collaboration with Tom Whitehead at Intelligens. And we'll set the scene in terms of the particular problems that this addresses, describe the algorithm, and then in particularly go into a lot of depth around the applications to a practical ongoing drug discovery project to impute and predict data for very heterogeneous endpoints, including compound activities against targets, cell-based activity, and ADME properties as a project progresses. So this is the first of a series of different applications we're going to be talking and publishing about, and we'll hope you'll be able to join us. And so again, thank you very much for joining us today. It's been great to see so many of you on the line. If you do have any questions, please feel free to contact us at info@optibrium.com. As I say, we'll stay on the line and try at least get through some more of the questions here in the panel. But for those of you who asked a question that we don't answer, we'll certainly get back to you as quickly as possible with an email. And finally, just a reminder that this whole presentation will be available as a recording on our community website at optibrium.com/community. As soon as we can download and produce the video, we'll get it up there and send you a link so that you can view it again or share it with your colleagues. So again, thank you all for joining us. I can still see we have more than 100 people on the line. So let's get back to a few more of these questions if you're willing, Mario, and we'll try and cover a few more before we wrap up.
Alrighty.
Let's just have a quick look through here. Oh, okay, I'm trying to choose people who haven't left the line. So another UGT-related question. How well does the glucuronidation model cope with aromatic nitrogen glucuronidation?
Quite well, I would say. We had a lot of those nitrogens actually, well, not a lot compared to the phenols, but a fair amount of such nitrogens in the data set, and yeah, no problems there, I'd say.
Great. Okay. We've got a very technical question here, but a very, very good one indeed. Oh, unfortunately, the questioner has left, but I'll ask it anyway for the audience that remains. It's a question about test sets, which is how the test set was generated. Is it random and clustered? I think in all cases it's a clustered test set, but quite rightly points out that a test set that's chosen to be as different as possible from the training set is a more stringent test than a random or clustered test set. That is absolutely the case. Here, I guess there are 2 points I would make. The first is that the methods that we're using are generally much more transferable because they're based on quantum mechanics. We don't have the same issue, to the same extent anyway, with domain of applicability of the models. You know, physics and Schrodinger's equation applies pretty much everywhere. So we're not quite as worried about this domain of applicability question. We're also limited by the sizes of the data sets that are available here. And so therefore, you know, we don't have the ability to sort of hold out a completely different set of compounds that would be sufficient for a test set. So we'd love to do that. But the saving grace is, of course, these P450 models have been applied for over 15 years in practice to drug discovery projects, which are in clearly very different areas of chemistry and in constantly evolving areas of chemistry with a very high success rate. And so, you know, we have very high confidence in the generalizability of this method, even if the specific test sets we've been talking about are not designed to test extrapolation in chemical space. All right. Let's see. We've got a couple more people still on the line. That's a good question. There's actually 2 people have asked about esterases. There's increasing interest in esterases and hydrolases, excuse me, particularly for peptides. And someone else has mentioned in terms of esterases and modeling stability of esters in the plasma. So I guess this is a little bit of a strategic question. Certainly there are many enzyme classes that we can cover. Esterases are certainly on the list. I guess the big strategic question is which are the highest priority? And as Mario said, I think right now our primary focus and the greatest interest seems to be in aldehyde oxidases. Here's another great question. Is N-oxidation leading to Ames positive metabolites covered by any of these oxidation models?
Sorry, could you repeat that one?
Yeah, absolutely. Is N-oxidation leading to Ames positive metabolites covered by any of these oxidation models?
I think that is a question for Peter, but I do believe so.
Yeah, absolutely. So, yeah, I think certainly N-oxidation by FMOs and by P450s are covered, certainly by the models. I guess the next question is, are they likely to be Ames positive? And here's where another element of our collaboration with LASA Limited becomes very important, because with the Direct Nexus module that we work in collaboration with LASA to include within StarDrop, one can take the products from the models that predict metabolism and actually run them through Direct Nexus to see if any of them trigger sort of alerts for Ames mutagenicity experiments. So that combination has a great deal of potential. Okay, well, I think we are just about getting to the end of the questions for those people who are online. So I'm going to take the opportunity to thank those of you who still remain online and have seen us through to the end for sticking with us. Thanks to everyone for joining us today, and we hope we'll see you at the next webinar. So thank you very much.